Okay, hello everyone. Good afternoon. Um, so today we're going to talk about something a little bit different. I think as the years have gone on in teaching this class, I've sort of leaned more and more towards doing a lot more predictive modeling. So really thinking about how we are constructing models that basically allow us to do like good out of sample prediction. And I think that this type of approach is kind of good for many different reasons, but sort of generally, this is more of an approach taken uh, by statisticians and in machine learning. As you take certain approaches where you may have really big data sets, really these large scale rich data sets where you have like a whole lot of explanatory information and power, and you're trying to kind of figure out the sort of best use of that to, predict a particular outcome. So the kind of flip side of that coin, and sort of the sort of converse of that approach, is more in the domain of like economists and econometricians, where they care a lot less about predictive power, and they are focused more on trying to establish causal relationships. And so I've never really sort of totally cut that out of the class. So today we're going to focus on thinking about causality. So I'm sure all of you guys have heard this expression: correlation does not equal causation, which is true for the most part, but correlation can oftentimes be a sort of starting point in order to establish causality. But you should not have a misconception that they are the same thing, certainly. And so even if we think about, so one of the examples that we've been talking about in class is this wages data set, right? Where we were looking at basically the effect of age and the effect of race and gender on your wages. And this is where a lot of sort of the nuance comes into the interpretation, right? Because, just because we observe these differences between, say gender, in the sort of final wages outcome, that doesn't mean that the gender itself is the causal effect of that would lead to that difference in wages, right? So there are lots of underlying factors that have to do with social or cultural norms and historical precedent, all of this kind of stuff that we are kind of capturing through that gender variable. But for example, like if you were to like change your gender, that doesn't mean that you automatically would just have a different wage, right? So that's what we kind of mean by determining the causal effect is that if you actually changed your input parameter, that would directly lead to a change in your outcome. And so that is one of the mechanisms that is already always very kind of elusive and hard to get at, but is really important when we think about things like policy interventions, because like we want to know, you know, what may happen if you introduce a specific policy, and in order to do that, you need a really good sense of like the causal mechanisms that could be getting affected. And so we're going to explain how we sort of get to that today. So correlation is just a relationship between two variables, whereas causation is one event is the results of the occurrence of the other event. Okay. So I think one of the best ways, at least when I was in grad school, to kind of really understand this concept is kind of visually. And so we learned about this graphical model called directed acyclic graphs. And so this is a finite directed graph with no directed cycles. In other words, it's a graph that can't loop. And so this is also known as a DAG. And so we're going to use this to demonstrate direct causal events. And so this is also known as graphical causal models. So essentially these are like these little networks with bubbles essentially representing each variable, and then arrows going to other variables to show which ones which variables are affecting specific variables and outcomes. So let's do an example of this. Okay. So let's take an example of heart disease. And I'm going to draw out a little model here. So heart disease can be caused by inflammatory immune response. This could be a result of, say, gum disease, which is directly related to the frequency of brushing teeth. Okay, and just for a little bit of nomenclature, so in terms of variables, we could call this a parent to a child. And then more generally, going up the chain are ancestors. And then going down the chain, you have descendants. Okay, so what do you guys think? So looking at this model, basically I'm saying that so the more often you brush your teeth, the less likely you have gum disease, and the less often you'll have this inflammatory immune response, which leads to lower incidence of heart disease. Therefore, brushing your teeth leads to lower, directly leads to lower heart disease. Yeah, so I guess, does anyone have any thoughts about that? Does that make sense? Or you want to say nay?
There might be room for like maybe someone who frequently brushes their teeth also takes care of themselves more in terms of other health or self-care activities.
Yeah, okay, so great. So let's say that you are a health conscious person. And so someone who's very conscious about their health may brush their teeth more frequently, but they also have a higher frequency of exercise, or they have a better diet, so amount of fat / red meat in diet. Okay. And so that is exactly right. So you can see that there are sort of multiple avenues to this heart disease outcome. And so if I, for example, went across a sort of large population of people and I did a survey and I asked them about how frequently they brush their teeth, you get a whole bunch of people with these heart disease outcomes. And if you try to make a conclusion about the causal effect of the frequency of brushing their teeth, well, unfortunately, it could be getting confounded by other factors having to do with how conscious they are about their health. And therefore, you may have a whole bunch of people who brush their teeth very often that have low incidence of heart disease, but they also exercise a lot and they all have really good diets. And you therefore can't say anything about the causal relationship of the frequency of brushing their teeth because there are these other effects that could be leading to the explanation of that outcome. However, if we can somehow remove this, or control this relationship, if you did the same kind of survey, but you only got people who who have a similar sort of health consciousness, so that either they all sort of exercise with some frequency and have a similar sort of diet, then it's possible that you could isolate the effect of frequency of brushing your teeth, and thereby sort of get at this sort of specific pathway without the influence of these confounding factors. And that is, in principle, sort of one of the more common approaches to figuring out causal relationships. And so, you know, we'll look at a particular implementation of this, but just at a high level, kind of be reminded that whenever you are trying to do these like causal mechanisms, that you should think carefully about the relationship between the thing that you're trying to, or the causal relationship you're trying to establish and all the other variables. And it becomes very much kind of more art than science, because you're trying to oftentimes you have to justify this relationship qualitatively, and that you've like been able to control for all of the confounding factors or sort of unexplained errors that could be correlated and getting to the response variable that you're interested in. Okay, any questions about this? All right. So let's go ahead. So let's talk about this in a more sort of general way. So the general problem is that if we want to establish some kind of relationship between my x and my y, this is ultimately what I want. I want to understand the causal relationship between x and y. You will usually have some kind of unforeseen error term, which confounds the effect. So U confounds effect of x on y. And so this is exactly kind of like this previous example, right, where x is brushing your teeth and U might be health consciousness. And so you have this kind of variable that can lead to changes in your response variable through an indirect path, and could also be influencing your x, right? And so what we want to do is a strategy called identification. So this is the strategy to remove the confounding effect. And determine the causal effect. So there are 3 common strategies with which you can perform identification. So 1, block all indirect paths from X to Y, but leave all direct paths open. So this is known as a backdoor strategy. 2, all direct paths from X to Y pass through a mediator variable. This is known as a front door strategy. And the last one is use an instrumental variable, which you may have heard of if you've taken any econometrics, which affects X and affects Y only through X. So I can give some examples of this. 1 is a little bit less straightforward, but for 2 and 3, essentially what you'd be doing, so this is for 2, if we have our X and our Y, you would have a mediator variable. So if you think about, actually, if I were to go back to this chart, one example is gum disease. So let me get rid of these. So this, in theory, could be a mediator variable. So if we were able to observe incidence of gum disease, then you could use that as essentially this sort of extra control that interrupts that interrupts the relationship chain between health consciousness and heart disease. But you cannot you can't have something like this. Otherwise, you run into the same problem as before. And so in our particular example, this may not necessarily be the best because this could be getting affected by other health conscious activities. So like, for example, you could argue that there's probably a relationship between gum disease and the type of food that you eat, which is influenced by your health consciousness. And therefore, this may not be a very good mediator variable. So selecting the right sort of variables can definitely get pretty tricky. And then another example, so I'll have to make a new sort of page here, but if we have this guy again, so this is for the IV example, and IV stands for instrumental variable. What you want is, actually I'll write it as IV. All right, so your instrumental variable, so this would be valid example. So your instrument acts on your x, and it does not act on your y through any pathway other than through x. And so that this is something that oftentimes you would have to sort of qualitatively defend, that your instrumental variable is valid. If you had something like this, so this was z, this would not be valid, because it is acting on your explanatory variable through the effect of some other variable, and as a result, you don't know if any changes to y are the result of your x variable or of your z, right? So that's why you want only the effect of IV going through, and it's the exact same principle, because on the left case we've isolated the effect of y, because even though we know that there are influences of like other variables on x, as long as you've controlled for only the changes that you're observing from the instrumental variable, you have then isolated changes in x to this thing that you can measure, which would sort of be able to eliminate any of the effects from your unobserved error terms, for example.
So in this case, the IV can't have a relationship with you either?
Yes, that's right. So if you're, well, actually, if you're unobserved, if the unobserved term has an effect on both x and on IV, then that's right. Then it wouldn't work, because you don't know whether or not the changes in x are coming ultimately from you or from IV. These are always hard to come up with like a good example for, but essentially, right, you want to be able to observe something that's changing x without changing your instrumental variable. Otherwise, you can never be sure where the sort of ultimate causal effect is coming from. Yeah, so this is not valid. And that can be really tricky, because unobserved variables is it's the set of like all the variables that you're not controlling for. So you have to have a lot of confidence that you're essentially breaking that relationship when you make this model. Okay. Any questions about this?
I have a question kind of related to where we have like your IV can't be related to Z if Z is related to Y.
Yep.
I would assume that for most variables, it's if X is related to Y, then our IV could be related to like Z, which is related to W, which is related to Y.
Yeah.
So like
Doesn't
how
work.
many steps away do you have to be?
No, yeah. So you can't have, you know, Z1, Z2, Z3, whatever variable. Like IV can literally only operate on Y through X. Now you are allowed to do things like you could have IV going to Z1, Z2, X to Y. Because it operates on Y through X at some point, but as soon as you have any connection here, this is no longer valid. Yeah, if that makes sense.
Yeah, and this might be along the same lines, but if I was interested, say I had like X1 and X2, but I am trying to include an instrumental variable for the relationship between X1 and Y.
Yep.
Is the relationship between your instrumental variable and X2 a problem? Like, does your model just need to stick to the relationship you're interested in, even if you think X2 is meaningful to the model?
Yeah, so okay, so this could be this model could be an example of something like beta x1 plus beta x2 equals y. So you could have an IV like this, and this would be perfectly fine. This would not be fine.
Thank you.
Yep. And so, and hopefully just to sort of clear any confusion, like, again, the entire validity of your instrument is making sure that that sort of pathway is robust. So IV operating on X, or the effect of IV on Y has to only happen through X. That's basically the sort of definition of your instrumental variable for you to have a valid instrument. One thing that I will kind of note is that even if the instrument is a good, so I'll sort of quote valid variable, if it is weak, it may lead to lots of noise. So large error. Error term, which means not great for prediction. And in fact, at reasonable sample sizes. Sometimes you get better predictions, you get even substantially better predictions, much better predictions with a biased OLS model versus unbiased IV regression. So what this means is that the relationship from a qualitative standpoint, you could have a perfectly valid instrument that people would have a hard time kind of arguing against because you've made a good case that like your IV affects your X or your IV affects Y only through X. But if the relationship between IV and your X is fairly weak, then your final model could have really large errors. And the quality of your model could be like significantly diminished, even though you have arguably an unbiased estimator. Yeah, let's see, one example of this that sort of coming to the top of my head is actually from a paper we published a really long time ago where we wanted to look at the effect on let me write out the model actually. So this would be VMT. So this would be miles driven as an effect from gas prices. And we want to get the causal effect of gas prices on how much you drive. So there's a whole bunch of other variables here. So if I just had this model, I guess, can anyone chime in as to reasons why they think that this beta may not be a causal relationship? Can anyone think of maybe, well, can anyone think of anything in the error term that may affect the gas prices?
Is it maybe like a bi-directional causality? Like if
Yeah, yep. So that is a common one. So bi-directional. So like you can think about asking yourself, if everybody stopped driving, would that affect gas prices? And so, you know, if that's the case, then your beta may be actually saying something like, it's actually just a relationship, but it's more that the gas prices are changing due to VMT rather than the other way around. And so in this particular example, this is a common, in this sort of VMT to gas prices is a common argument in looking at that relationship. So how would we maybe deal with that? You would need something that would affect gas prices, but not VMT, right? You would need some kind of IV that that didn't have a relationship between here, so that you could observe changes in gas prices and thereby changes in VMT due to what we know as gas prices and not sort of the reversed cause. And yeah, so in the paper that we had written, this particular example that we used was, so VMT was actually VMT in Pennsylvania. And the instrumental variable was gas refinery essentially shutdowns due to hurricane activity in the Gulf of Mexico. And so we know that the supply of gasoline is directly affected by these refinery shutoffs, and therefore you observe some gas price changes in your system. And then we kind of argue that hurricane activity happening in like Texas and in the Gulf of Mexico doesn't really change the aggregate travel demand happening in a state like Pennsylvania, which is, you know, thousands of miles away. So this is, you know, arguably one strategy that could be used to disconnect the relationship here, because you've now established a connection to gas prices that sort of essentially breaks that relationship. So that's just sort of one example of the type of instrumental variable that you could come up with to address this causality type of problem. And you can also see how a lot of the justification for these instrumental variables is really qualitative in nature, right? Because we're kind of making this argument that like, oh, our choice of this variable, you know, doesn't have the impact on these variables, but it does have an impact on these variables. And so if you attend a lot of like economics seminars and talks, I feel like half of them are just people defending their instrumental variables, because it is so critical to establishing this causal effect that folks are always striving for. Okay, so the next part of class, we're going to show how to actually implement an instrumental variable regression, and we're going to take a look at a practical example in R. But before we do that, let's take a quick break for 5 minutes. We'll start again at 3:01. And in the meantime, if anyone has any questions on this material or any other course-related questions, we can do that during the break. Okay, let's continue onwards. So we'll look at example now of a model that is examining an outcome of BMI, which is your body mass index. And so we'll have a whole bunch of variables to look at that we can control for. So income, age, gender, pregnancy, so whether or not you're pregnant, how that affects your BMI, education, and whether or not you are a smoker. And in this particular example, the thing that we will be interested in trying to identify the causal effect is the effect of being a smoker on your BMI. I think kind of obviously there could be right, some kind of unobserved variable, maybe we'll call it social opportunity, which is acting as your confounder here, because this your social opportunity may dictate whether or not you're a smoker, whether or not or what kind of education you have. It could dictate, you know, things related to your income, maybe even pregnancy, right? And so, you know, just running a model of, you know, BMI on beta income plus beta age and so on and so forth. If I were just to do this, your beta is probably not a good indication of causality, right? And so we need to think of some kind of instrumental variable that will affect whether or not you're a smoker, but not through any other sort of connection. Okay, so, oh, hang on. I accidentally deleted this part. Just get rid of this here. Okay, so for our IV, we're going to consider 3 variables, 3 candidate instrumental variables. And so even before we talk about how we do that and then show the application, yeah, it would be, I think it'll be good to kind of discuss what we think will work or what we think won't work and sort of for what reasons. So cigarette tax as an instrumental variable, unemployment as an instrumental variable, and then whether or not you're separated or divorced as an instrumental variable. Okay, so let's actually start with unemployment. So can anyone tell me why they think this might be a good or a bad instrumental variable? Through this model.
Education, may have a relationship and income. I don't know.
Yeah, exactly. So if I were to draw this unemployment, yeah, you definitely could likely find a relationship between unemployment and smoking, right? And so through that, it would affect your BMI. And so we do want that as part of the instrumental variable, but being unemployed likely also affects your income, and it could actually be like, for example, education could be affecting unemployment. And so you've got these relationships going both ways, kind of education through your unemployment, going to your BMI, but also affecting it through smoker, right? So through this pathway here, like so. Or it could be affecting your BMI through income. Yeah, that's right. So unemployment is probably not going to be a really good instrumental variable. Okay. So then what about for if you are separated or divorced? Right, so maybe being divorced, you're kind of more stressed in general, therefore you have a higher proclivity to be smoking. And so we can maybe establish some kind of weak relationship there. So is this a good instrumental variable or no? Anyone? No volunteers?
I mean, the one that seems most obvious to me is that older people might be more likely to have been separated or divorced.
Yep, okay.
So age might be
So
related.
you could have a relationship like that. Yeah, that's right. Probably whether or not you're separated or divorced could lead to lower or higher incidence of pregnancy, I guess. It's possible. So again, probably several avenues with which you'd be operating through that would not make this a valid instrument. And lastly, we've got a cigarette tax. And so that just makes smoking more expensive, and therefore, you know, if the tax is high enough, I guess you could assume that there's going to be some effect on whether or not someone is going to be smoking. However, I guess it's somewhat unlikely that the cigarette tax would be probably operating through any of these other variables. And so in this particular example, we could argue that cigarette tax is going to be a valid instrument to try and determine the causal effect of being a smoker on BMI. All right. So the way that we implement an instrumental variable regression, so I'll show one common method known as the two-stage least squares regression, also known as 2SLS. So this is a regression that's performed in 2 steps. So first stage, regress the causal variable of interest on the instruments and the remaining exogenous variables. Second stage, regress the original outcome variable on the exogenous variables and the predicted value of the causal variable in the first stage. So in other words, in step 1, we have xi, so this is our causal variable, and then we regress this on let's say zi, and you'll have a particular error term. They usually use this Greek letter that I can never draw. And then in your second step, you have yi equals your beta, not of x, but of x hat, importantly, plus your error term. And so you run your first step regression and then your second step regression, and this beta will be different than if you had run it for just x, for xi. All right, so let's move on to RStudio to show implementation of this. Unless there are any questions. Okay.
Yeah, just a quick question. I was wondering, like, is being a smoker somehow supposed to be related to social opportunity, like you said in one of the previous slides? So there was a confounder, and that's cater to. So how does?
Yeah, so actually here I'll go. Oh, actually it's probably disappeared now that I did that. So you have your social opportunity as like a potential confounding unobserved error term, which affects like education and income, for example, right? But also affects whether or not you're a smoker. You just want to find some kind of instrumental variable that is that would be disconnected from this confounder, right? So the presence of a cigarette tax doesn't have anything to do with the fact that you have social opportunity or not, right?
Yeah, that makes sense. Thanks.
Yep. Okay, one moment. This guy, here we go.
Alan, I also wanted to ask if you're going to use a new data set, do you mind sharing that on Canvas?
Yes, so that you guys can follow along. Let me do that right now, actually, so that we can. Okay, give me one moment. Yeah, I'll do that in the future. Okay, so it's uploaded to Canvas. I'll give you guys 1 second to go ahead and grab that, and I actually have to move that data set as well into the proper location. So this way you should be able to follow along. So you should see a data set called ps6.txt. And that is going to be the BMI data. So ps6.txt. It's separated by tabs. So you have this /t, and it has a header. And then I am just going to go ahead and drop any incomplete data from the data set. So we'll go ahead and have a look at this. So we've got 14 variables. We've got a FIPS, which is the location, the year, income squared, age squared. So we'll actually include those terms in the regression. Gender, dummy variable, pregnancy dummy variable, education, another dummy variable, and then whether or not they're smoking. The BMI is the outcome that we're interested in, and then we've got a couple variables that we talked about considering as the IV. So whether or not they're separated and divorced, whether or not they're unemployed, and then the cigarette tax. Okay, so let's go ahead and look at the simplest example first, our OLS. So this is our standard linear model, and we're going to do BMI regressed on income squared plus age squared plus whether or not they're or their gender, whether or not they're pregnant, their education, and whether or not they're a smoker. Okay, and so we can go ahead and look at this. Okay, and we can see that the BMI is most closely related to age and gender, and looks like most everything else doesn't have much of an effect. And smoking increases BMI, but it's not statistically significant, so we're not sure necessarily whether or not it actually has an effect. Okay, so let's look at how we would implement this for the unemployment instrument. So we have our first stage model. And the way we do that is we regress on the causal variable of interest, which is whether or not they're a smoker. And we put in all of these variables from above. So I'm just going to copy and paste it like so. So all of your exogenous explanatory variables, not including smoking itself, obviously, and then the instrument, which is this unemployed variable. Okay, and so now that we've run that model, we now want a prediction of my x's. So in other words, the prediction of whether or not they're going to be a smoker based off of the first stage model. So I'm going to do BMI data. I'm going to add a column called smoke IV, and this is going to be for the unemployment variable, and this is going to be where I simply predict the stage 1 model.
One question here.
Yes.
Smoke is a factor variable, have 1 or 0. Do we use a linear model or something like logic model or something like that? Logistic?
Yeah. Yes. So yeah, we're going to talk about logit models pretty soon, actually. So what Daniel's talking about.
In this stage, we only need to know if there are any relationship.
Yeah. So it's hard to come up with examples of IVs. Well, look, getting a good data set for this. So yeah, the fact that it's 0 to 0 or 1 is not ideal. I will say, kind of, and we'll talk about this a little bit more when we get to logistic models, is that it's not entirely inappropriate to do regressions on 0 to 1 outcomes when we think about sort of being within the bounds and thinking of sort of average effects. The outcome variable itself is going to be sort of nonsensical, right? Because it's a sort of either or type of thing. But qualitatively, you could still get like decent relationships. So yeah, I'll say this is probably not the most ideal example from that perspective, but it's still going to show us how to kind of implement this 2SLS thing. But yeah, I think ideally you might do like a logistic regression approach for maybe the first stage.
Okay, thank you.
Yeah. Yeah, so just to kind of clarify what he was talking about is that we haven't discussed this yet, but if I look at the BMI data, like we're actually making a regression on on this column here, which you can see is, I can't scroll for some reason, but you can see BMI data, dollar smoke. So you can see that there's only two possible values at 0, 1. And it's not always a good idea to do a linear regression on these discrete data points. And we'll talk about other approaches to do this later on. But for this example, we are, because getting good IV examples is difficult, unfortunately. So once you're done with the first stage, you can jump on over to the second stage. And we just add everything back in. And this time, instead of putting our, like in the OLS where you have the smoking variable, we actually put in the predicted value of X here. And so now I can go ahead and look at this. And you can actually see in this case, what did we say before? That gender, gender and age were the important ones, but now it looks like it's pregnancy and smoking and the effect through the effect of that. This would be arguably, if this was a valid instrument, the causal effect of smoking on your BMI. So here's one of the things to keep in mind is that, like, when I think about this model versus the regular OLS, you know, there actually are a couple tests that can tell you whether or not the instrument is strong or weak. In other words, that tells you something about the sort of like correlation between your instruments and your causal variable. But the validity of an instrument, again, is more sort of on the qualitative basis. And there's not much that you can look at in terms of the diagnostics here. Like if I were just looking at like R² or statistical significance or other, you know, other metrics that we've discussed, none of those are really going to tell you anything about whether or not the instrument itself is sort of valid. And so it doesn't do much good kind of comparing against your sort of original OLS model in that case. So that's important to keep in mind, is that, you know, however good the model may look, you need to sort of back up the quality of the instruments or the validity of the instrument through other means. And so now let's take a look at the cigarette tax instruments. So we're going to do the exact same thing, but this time, instead of using unemployment, which we kind of suspected would not be a good instrument due to the fact that it's probably acting through a couple of your other explanatory variables or has some kind of relationships with other explanatory variables, we're going to look at cigarette tax. So our first stage is going to be regressing smoking with all the other variables plus your cigarette tax. And then we can see here all of the effects of those variables. I should mention that by controlling for all of the other sort of exogenous variables, this is why you're including them in the regression. In the first stage regression, you're essentially helping to essentially control for any collinearity effects with your causal variable and everything else in the second stage. So it really sort of helps negate any arrows from your x2, x3, x4 on your x1 going to your y, which is why you include that. We need to make a new column here, which is going to be the prediction of our cigarette text model. And we'll go ahead and take a look at the second stage here. So I'm just going to go ahead and copy and paste all of this. So all of the regular exogenous variables plus your IV or your causal variable that has been instrumented. So you're looking at the predicted one from the first stage. Oop, to run all of this, huh? Okay, so we can see here that this is what one might argue is kind of the causal effect of this of smoking, because now we've included this cigarette tax instrumental variable, and so here is our estimate. One thing that I'll quickly note is that if you do this kind of manual procedure to calculate your 2 SLS, you will have the correct values for your coefficients. But the standard errors actually need to be calculated in a slightly different way. We won't get into sort of the theory about that, but just know that these standard errors are likely an underestimate of the true standard error. And so what I've been doing here is really mainly just to show you kind of the back end procedure of doing the 2 SLS. But in actuality, there are packages, of course, that will do this for you. So we're going to look at that. Oh, apparently I don't have this package installed. Don't know how that's possible. But, oh, AER. So we're going to show you guys an example of a package that does the 2 SLS for you. And that package will give you sort of the correct standard errors. So instead of LM as the linear model, this uses the function IVReg. And the way this works is pretty similar. So we're going to have BMI, and then we're going to put in our explanatory variables. So much in the same way. And then what you're going to do is you're going to leave your variable of interest that you're trying to determine the causal effect for last. And then you have this, what we use as the OR statement in the equation, and then you're going to put in the variables that you would be using in the first stage. So income squared plus age squared plus factor female plus factor pregnancy, factor education, plus cigarette tax. So in this case, you're kind of, you are essentially writing out the two stages of your 2SLS regression all in one line. So this one, as you're used to, plus this one, which is the sort of way that you notate the first stage in this function. So if we run this, it should give some results that we can then look at. And there you go. And in this case, a lot of the standard errors should be a little bit higher than what you've seen before. Don't worry about the R squareds. They're not, when you do the 2SLS, it's just going to be kind of nonsense. That's not a metrics that this particular package reports accurately. The walled test. The walled test is essentially like a version of the F test, but it's for the instrument. So it tells you something about the strength of the instrument, essentially. And you can kind of interpret it in an analogous way as an F test. Okay, so any questions?
I have a question. Is it possible to tell from like the coefficients or the significant level of the coefficients to say how strong the causal effect is, or how good an instrument is, like from the result of the model?
Yeah, okay, so the interpretation of like the causal effect here, for example, we can say you can interpret it much the same way as any other sort of variable. And so in this particular case, I know this is like not the greatest example. Unfortunately, right, it's like it's not statistically significant. And so we can say that this model doesn't show like a real causal effect because it's not statistically different from zero. And so the way that you would do the interpretation of the causal variable is kind of the same interpretation that you would do with OLS, assuming that the model is good and all of that. Okay, and so then when you ask about whether or not any of these models tell you anything about whether an instrument is good, so okay, I guess the kind of adjectives that I would describe are whether or not the instrument is valid. In other words, that graphical acyclic models that we drew. So let's talk about validity first, and then let's talk about the strength of the instrument. So validity refers to kind of our confidence in the relationship. In other words, all those arrows being correct. And so a valid instrument will make sure that IV operates on your Y only through X. And in that case, there are not very many sort of diagnostic tools to kind of demonstrate validity. I mean, you can through through a series of looking at, for example, conditional distributions and to determine whether or not independence is acquired. But it is necessary but not sufficient for demonstrating validity, because you could always be there could always be sort of other omitted variables that you'd never be able to kind of really control for when you do that kind of test. And I so rarely see those kind of tests being done in the sort of econometric literature. And so usually the justification is not looking at these specific tests of conditional distribution and independence. It is all about this qualitative argument for determining that the relationships are correct, essentially. So that's on the validity side, which I think is a lot kind of harder to prove. And then on whether or not the instrument is strong, that all has to do with essentially the relationship between your instrumental variable and the variable of interest. So in this case, it would be the relationship between cigarette tax and smoking. And in that case, there are lots of different tests to look at how strong or weak that instrument is. The Wald test is one of those, and that will tell you essentially that there is, it's kind of like saying there's like a high correlation between cigarette tax and smoking, essentially. Yeah, and so there's actually a variety of different measurements for the strength of an instrument that you can look at.
Okay, thank you.
Yep. Okay. Anybody else? All right. Yeah, so that's actually we'll actually end early today. This is kind of all I have for today's lecture. And again, kind of to back up once again and think kind of holistically about today's lecture, I think that this is probably the sort of most different type of material that we cover in this class. As I mentioned before, most of the content has leaned more in the direction of looking at predictive models as opposed to causal models. And I guess I'll give you guys a little bit of kind of my personal perspective on this, in that, you know, when a lot of causal models, where you try really hard to get these like good instruments, you know, qualitatively, you do a lot of this justification for figuring out these causal relationships. But at the end of the day, a lot of times, especially when you have weak instruments, the models themselves end up being fairly weak. And again, this is kind of my perspective. It strikes me often that like when you build these type of models and you want to say something about a particular outcome that you've determined, if your ability to say anything about that outcome is really weak, or very inaccurate due to the nature of how like instruments work, like at the end of the day, it's kind of like asking what's the value of determining that relationship if your estimate of the outcome is often wrong, right? And so you can have a valid instrument and possibly even a strong instrument, but your model could be, for example, predicting a lot worse than like a biased model would. And so, you know, I've kind of always struggled with understanding the value of that. And so this is a little bit of my own bias, but I do feel that predictive models have, I guess, a sort of different a sort of different set of values that I think make a lot of sense when you're doing data analysis. And so, like, if you went and talked to an economist about this, they would for sure completely disagree with everything I'm saying. But I just wanted to give you some of my perspective on sort of these types of models. So, okay, great. So we'll end here a little bit early, and I'll stick around extra for any questions about the lecture material or about the homeworks if anyone has any lingering questions, which will be due on Wednesday.